Hi, this is Professor Fernandez, and we are going to talk in this video about Module 2 in Lesson 6. We will spend the video talking about the multivariable chain rule. So let me just scroll down really quick to the actual statement of the multivariable chain rule. What is, I will refer to it as the one implicit variable case. I'm not going to go through the whole statement for now because there is one thing we should talk about before we talk about this theorem. And this is this bit right here. It says, let a bunch of stuff and z equals f of x, y be differentiable functions. We know what it means for single variable functions to be differentiable, but so far in the course we have yet to talk about what it means for a multivariable function to be differentiable. So let's scroll back up. This is why the chain rule statement is on the following page, not the first one in this video. And let's talk about differentiability in the multivariable context. To do that, let me just remind you what you know from single variable calculus. So recall from single variable calculus that a function f of x being differentiable was the same thing as saying that f prime of x exists. So, you know, we might be talking about differentiability at a point, f prime of 2, let's say, exists, or on an interval, f prime of x exists, you know, between x equals 1 and 5. But that's at the core what differentiability meant in the single variable context. The question that concerns us at the moment is, what does differentiability mean for a multivariable function like f of x, y? And it's not an easy question to answer because now we have two variables that can change. And let me make this an even slightly easier question at a point A, B, so that we don't have to talk about domains yet of differentiability. So we have two variables changing in f. We have x and y. In the previous video, we talked about partial derivatives. So maybe you might have some notion that partial derivatives are involved in this answer about differentiability. And indeed they are. A full answer involves tangent plane concepts, which we are going to actually get to in a future lesson. But for now, based on the limited intuition we developed about differentiation in the multivariable context, here is a theorem that tells us sufficient conditions for a function, two-variable function, to be differentiable. And as you'll see in a minute, it has to do with the partial derivatives we talked about in the previous video. So let's see what this theorem says. The theorem says, suppose f is a function defined on a disk in R2, and let AB be in this disk. If fx and fy, remember these are the partial derivatives with respect to x and y, exist for all points in D near AB, and so another condition, fx and fy are continuous at the point AB, then the conclusion, f is differentiable at the point. So the way I want you to think about this theorem is that the conclusion is what we're after for now, for the purposes of talking about the chain rule, what I started off with at the beginning of the video. We're after this notion that we want to have a rudimentary understanding of differentiability of two variable functions at a point. This theorem tells us that in order to get that conclusion, there are some sufficient hypotheses that we have to make. We need to know that the partial derivatives exist near the point that we're interested in, and that they're also continuous at that point. Now, of course, for special types of f of x, y functions like multivariable polynomials, these conditions will always be met. Or for other smooth and continuous type functions like exponentials of multivariable polynomials or compositions of continuous multivariable functions, these conditions will always be met. So I don't want to give you a sense that this theorem is restrictive with these two assumptions. But I do want to point out that there are assumptions in this theorem that, you know, we should check before we use the theorem. So to do that, I'm going to go through this example to show you how you would check this theorem and then conclude from it that a particular function is differentiable at a specific point. Okay, so to do that, what do we need to do? we need to satisfy all the hypotheses. First of all, we should calculate fx and fy, make sure they exist near this point, and then separately we should make sure that they're continuous. So the first thing I will do is calculate df dx, del f dx, also fx, just a quick little review there of notation. And remember the way this goes. So I'm going to treat y in here, there's the only y there is in the function, as a constant when I differentiate with respect to x. So this is then a product of x and e to the x times a constant. So I need to use the product rule. So derivative of the first, which is 1, times the second, plus the first times, and now I differentiate e to the xy. Because y is a constant, it comes out by the chain rule, and then e to the xy. This is like if I was differentiating e to the 4x, right? Its derivative would be e to the 4x times 4. So now I'm just differentiating e to the y times x with respect to x. So its derivative is e to the y times x times the y. So again, you see the 4 and the y playing the same role when it comes to this partial derivative. All right, so I have calculated fx, and I'm just going to simplify it a little bit so we can look at it a little easier. So that's what I get. And then I'm going to go off and calculate f sub y, partial derivative with respect to y, and then we'll talk about the hypotheses of the theorem, see if they're satisfied. So partial derivative with respect to y, if I zoom in here, now I'm holding x constant. So I might as well think of this function as something like 2e to the 3y, and then differentiate that. So I don't need a product rule because x, when I calculate df dy, is constant. So I'm just going to put off this x here, goes along for the ride, and then differentiate e to the xy with respect to y. Again, I use the chain rule that brings down an x. Okay, so if I thought of x as constant, this would be again the e to the 4 y, and I differentiated this, I would get this result. So very similar to what I got earlier, except now instead of pulling down the x, I pull down, or sorry, pulling down the y like I did here, I pull down the x. Great, so I'm going to simplify our answer here, and I get x squared e to the xy. Okay, so now we've calculated the partial derivatives, and now we can go back to the theorem and start checking the hypotheses. So first question, do the partial derivatives exist for all points near AB? And I think the answer is yes, right? So fx is a product of a really nice function, exponential of a product of nice functions, x and y, times a multivariable polynomial. So yes, for fx. And fy, similar thing. X squared is a multivariable polynomial, product with the exponential of a multivariable polynomial, yes. So second question over here is, are they continuous? Okay. And this one, you know, we haven't talked too much about the continuity of exponential functions, but we did talk about the continuity of composite functions in the video on continuity. So this is e to the xy, so we can view this as, if we call this h of xy, we can view it as h of xy is f of g of xy, where f, the outside function, is the exponential, and g, the inside function, is a multivariable polynomial. So we know that this is continuous everywhere. And we know from single variable calculus that this is also continuous everywhere. And moreover, you can evaluate the exponential for any t-value, 0, positive, negative, whatever you'd like. And the range of this could be 0, positive, negative, whatever we'd like. So if you remember back in the previous video, we had talked about continuity of composite functions. The statement that gets us that result had all sorts of conditions, and I've just effectively run through them verbally here, and they're all satisfied. So they tell us that this e to the xy is actually continuous on whatever domain this function is continuous on. which is all, all x, y values, the entire plane. So this is continuous. This is continuous. The product of these functions is continuous. For the same reason, this is continuous. So long story short, both fx and fy are continuous functions on all of R2. So that means that we have satisfied the last requirement of this theorem. So I'm going to put a little check mark there too. So that gets us the result. So therefore, f of xy equals xe to the xy is differentiable everywhere. We actually did a lot more than what was asked, including, in particular, at 1, 0. Okay? So, depending on what level of detail you would like to give, you might want to reduce the amount of writing that you do. You certainly wouldn't have to give every single little level of detail. But I would like you to understand why we need to check certain things, the hypotheses of this theorem, before, at least according to this theorem, we can conclude that f is differentiable at a point. Okay, so now that we have that notion of differentiability, or at least a result that gets us there, let's talk about the multivariable chain rule. So, excuse me, the place I want to go back to is to your single variable calculus knowledge of the chain rule. So recall that in single variable calculus, let's say I was looking at a function f of x. If I wanted to differentiate that, then it would just be dy dx equals f prime of x. Nothing special there. But suppose now that x became a function of t, so that my function is a function of t. But it's an implicit function. I'm not going to tell you what x of t is. I can still calculate dy dt, but I now have to go through x first. So in order to calculate dy dt, I have to do dy dx and then dx dt. So this is the Leibniz version of the chain rule, dy dx times dx dt. And this is the reason that the reason I'm showing you this version is because it makes it easier to remember the chain rule. One way to remember it is these dx's cancel, although they really don't in actuality, because that is not a fraction bar. It's just notation for the derivative. It's a very good notation, Leibniz notation, but it is actually not a fraction bar. It's not like 3 divided by 4, not that type of fraction bar. But the point is, it's good notation and helps us remember the chain rule. And then, of course, in this particular instance, we know that dy dx is f prime of x. So this is the Leibniz view of the chain rule from single variable calculus. So the question is, how do we then generalized to z equals f of x, y. Okay, so if I take my function and I add one more variable, and then I kind of do the same thing that I did over here. What if I now have x become a function of t and y also become a function of t? Then what is dz dt? The answer is down here, but don't look there just yet. I won't tempt you. I'll do that. There we go. So how do I get dz dt? Well, notice the structure of what happened over here. What happened? I had the derivative with respect to the variable multiplied by the derivative of that variable with respect to t. So if you had to take a guess at what we would put here, I would say, well, the derivative of z with respect to this variable, well, that's the partial derivative, f sub x of xy. And then the derivative of this variable with respect to t, it's a single variable function. So that is dx dt. Okay? So that seems to be a kind of immediate generalization of this. We replace the single variable derivative with the partial with respect to x. You might say, okay, I'm done. But I would say, wait a minute. X has a t dependency, but so does y. So we have to somehow factor that in. And a very natural thing to want to do would be to say, well, okay, fine, I'm going to add the same thought process, the same line of thinking, doing this to y. dz dy times dy dt, and that adds this term. All sorts of questions you could come up with. You could say, why am I adding? Why don't I multiply? Why don't I don't know, add the square? Why, and those are all very good questions. And just like in single variable calculus, the derivation of the chain rule takes quite a little while. So I bet that the chain rule was never actually derived in your single variable calculus course. Instead, there was some version, perhaps an explanation with delta z over delta t, part of which we'll get to in the tangent line and tangent plane lesson. But some version of something like this was probably done in your single variable calculus class to give you enough intuition. And then if you were, of course, more curious, you could delve into the textbook proof of this. But I'm going to follow the same approach here for the same reason, right? We are less interested in this course in proving these things that you would do in an advanced multivariable calculus class. Believe it or not, such things exist. Or perhaps in a real analysis class, which is a possible follow-up to this. In this course, we want to balance the theory with the computational proficiency. All that being said, we have now provided, I think, enough motivation to get to the actual chain rule theorem. So let's read through this. Suppose x is a function of t, g of t, y is a function of t, h of t, and that z equals f of xy is differentiable. We're assuming that all of them are differentiable. Great, now we know one way to check if a two-variable function is differentiable. Awesome. Then the conclusion of this theorem is that z is a differentiable function of t. And the derivative of z with respect to t is exactly what we kind of motivated it to be. So first you take the partial of z with respect to x, then you multiply by x prime of t. You add to it partial of z with respect to y, multiply by y prime of t. So I'm going to illustrate that for you in this example down here. I am not going to, in general, continue checking these hypotheses for the examples that I do. At this point, going forward, I'm more interested in helping you develop computational proficiency. However, I may ask you to check these hypotheses as part of some question on an assessment. So I still want you to be able to do that based on the earlier work we did in this video. But for this example, the new thing is this, so I'm going to focus on that. So I'm going to say dz dt equals z sub x, partial of z with respect to x, times dx dt. And x here is cosine t, so the derivative of that is minus sine t. And then plus zy, partial z, partial y, times dy dt. Y is e to the t. Its derivative is just e to the t. Great. And then now this is me doing things, in a couple of steps. You could do it all in one line, but I think it's useful to split it up. It's easier to catch mistakes that way. If I go now to z and I want to calculate partial z, partial x, y would be a constant, and it's being added, so its derivative would be 0. I would just get 2x. So that's the first result. And then I go back, if I'm calculating dz dy, now I'm considering x to be a constant. Its derivative would be 0. And the derivative of y squared with respect to y is 2y. Okay, so I get to this point, and one thing I like to say in this course is, if you've arrived at what you think is the answer, I would just leave it like that. You could simplify, but unless you're going to be using the answer for something else, maybe there's a part B to a question or something, simplifying is generally about algebra, and I'd rather you learn some more multivariable calculus, right? And spend your time doing that than simplifying. So I'm going to leave the answer as is. We know what x is, cosine t. We know what y is, e to the t. So we could, if we wanted to, substitute these in here and get only a function of t, as you think we should have been able to do since we're calculating. Now notice that the d's here are not partials. So that is a signal that z is a single variable function of t. And in fact, you could have done this problem as a single variable problem by substituting in what x is in terms of t and what y is in terms of t. And this then yields a single variable function of t, which you could find the derivative of as you normally would in single variable calculus. So as a little exercise, I encourage you to compare what you get here with what you get there after you substitute cosine t there and e to the t there. You'll get the same thing. Great, so let's move on now to the next part of the lesson. Excuse me, the next part is thinking a little bit about what if things get more complicated? What if x is not only a function of t? What if x is a function of t and some other variable? Okay. Well, to do that, let me first show you a useful way to remember some of these multivariable chain rules. I'll scroll back up and I'll indicate. First of all, there's always what we talked about here, up here, right? This notion that these dx's, quote, cancel. They don't really, but it's useful to remember. Notice if I zoom in really a lot, the same thing is happening here, right? This is a partial, this is a dx, but you can think of them as canceling. This is a partial, this is dy, you can think of them as canceling. That's one way to remember the chain rule. Here's another way to remember this little formula. We can say, okay, so I have in these assumptions, z as a function of x and y, and x is a function of t, and y is a function of t. So I can draw a little tree diagram that you'll see this in many textbooks. So z is a function of x and a function of y. And x is a function of t, y is a function of t. And then I can write in here the corresponding derivatives. Because z is a function of two variables, then I'm going to write over here, and I'm going to ask myself, how do I get from z to y? Well, I have to take a partial derivative, because y is not the only variable that z depends on. And then similar question, how do I get from z to x? Well, I have to take a partial derivative here, because z depends on x and y. And then different answer though, how do I get from x to t? Well, in this context, x is a single variable function, so that's dx dt. And then how do I get from y to t? Well, similar thing here, y is only a function of t, so this is dy dt. Okay, and then this is another way then to remember the formula for the chain rule. So now if I want to get from z all the way down to t, I would say, okay, dz dt equals, well, I have to first traverse this part of the path. So that will end up giving me a product of these two terms, dz dx times dx dt. And then there is another t. There is another t, which is on this side over here. So then I have to go back and traverse this path, this one, and then this one. And that is going to give me a product of this and this. So I get plus dz dy dy dt. And then that is exactly the expression that we got from this theorem. Excuse me. So this is a way to kind of remember all the terms involved in a chain rule and how you put them together. So I'm going to use a similar approach in a minute when I talk about the two variable case down here. Okay, so if I go down to this setting, we're going to consider z to be a function of x and y as before. But now we're going to say that x is a function of s and t, and y is a function of s and t. So if I try to set up my little diagram here, it's going to look a little different. It's going to look like this. And then s and t. Okay. So similarly, if I want to now figure out what is the derivative of s with respect to t, I first have to realize that the ultimate variable here is not one variable. Not like in the previous case where I could, as you saw in the example that I erased down here, I could have written z as a function of t alone and then just differentiated it as a single variable function. I can't do that in this context because, and you'll see this in the example in a minute, s and t are linked in some way that might not allow me to separate them, and s and t in general are independent of each other. So what I'm trying to convince you of is I'm not going to write dz dt with the d's here, because z is not going to be a function of a single variable t. So what I have to start off writing from the get-go is partial z, partial t. And once I realize that, then I kind of do this path analysis from before. So to get to all the t's, there's a t here, there's a t here, I need to take this path, and also I need to take that path. And then let's fill in the derivatives that get me through each path. This is dz dx, and this is partial x partial t. Why is it a partial and not a dx dt? Well, because x is not a single variable function. It's a function of two variables. So in choosing this path over here, I am choosing to basically ignore the s. And that's essentially what the partial derivative does. So dz dt has a term that looks like this. And then now I have to follow this other path to do my analysis there. So to do that, I would start off over here and do dz dy, and then down here, partial y, partial t. So then that's the second term I have to add here. dz dy, dy dt. At this point, there are no other paths that lead to t, starting from z and passing through x and y. There's this one and there's that one. So there are no more terms here in the partial z, partial t expression. So that is, a good reason to add this view of the chain rule to your repository of ways to remember the chain rule, because you can imagine if I had added a third variable here, w, a third variable here, w, or a third variable over here, like q, the complexity could balloon very quickly. But if you can understand it in this way, it will be relatively easy for you to determine what terms there should be in the expression for these derivatives. That being said, this is as far as we will get a function of two variables, where each variable is itself a function of two other variables. That actually is able to explain a lot of real-world phenomenon, or just model it fairly accurately. Last thing I'll say here is that we could have redone all of this for partial z, partial s. Following this very same train of thought, we would have gone here and then here. That would have generated one term. And then here and then here. That would have generated another term. So that brings us to the statement of the chain rule, the two implicit variable case. And what does it say? Usual setup, x, y, and z are supposed to be differentiable functions. Then we have these partial derivatives. So the first formula over here matches what we just derived up there. And then this second, oops, I lied. The second formula here matches what we derived up here. And the first formula here matches what you can write down by having gone back to our analysis and followed this path and then that path. Okay? All right, so let me go ahead and show you an example of this so we can wrap up this lesson. So in this example, we are asked to find partial z, partial s for z equals this, x equals that, y equals that. Great, so partial z, partial s. We are going to write this down as z depends on x, partial z, partial x depends on s, partial x, partial s, plus z also depends on y, partial z, partial y, and then y depends on s, partial y, partial s. Okay, notice that I just, on the fly kind of gave you another way to remember the chain rule. It's always good to have multiple ways to remember it so that it's easier to not have to, to be nimble with what you have at your disposal to calculate using the chain rule. So any way we could do this, lots of ways. What I'm going to do is calculate partial x, partial s first. This is a logarithm, so that derivative is 1 over s plus t. And then I'm differentiating s plus t with respect to s. I just get 1. Remember there t is a constant because I'm doing partial with respect to s. Similar thing over here. What if I want to calculate partial y with respect to s? Well, then t is a constant. So this might as well be like 4s, and the derivative would just be 4. Y, no, you're right. T is the playing the role here of that constant 4. So partial y, partial s is just t. Great. And then we go back and calculate these two other ingredients. So if z is sine of xy, partial z, partial x, we're considering y as a constant. So first of all, the derivative of sine is cosine. And then we put back in the inside and then multiply by the derivative of this only with respect to x. That's y. Again, y is constant for the purposes of this partial derivative calculation. Great, so now I'm going to go back and do a similar thing, except differentiate with respect to y. Derivative of sine is cosine. We put back in the inside, and now differentiate this with respect to y. So x is the constant now. So that x pulls out. So plus x cosine of x, y. Great. So I've now differentiated everything, and I've gotten to the point where I have an answer. And again, I'm going to encourage you to just leave it as is. As before, we can substitute, if you'd like, what x and y are. You'll see that you'll get some somewhat crazy looking functions when you do that with cosine over here. But there's really no need to do that. The problem tells you that x and y are related to s and t, and it tells you how. So we can certainly add that information here if we'd like to. Great, so I will do a quick recap in this video just to make sure that I highlight the important points. First of all, we talked about this theorem for determining if a function of two variables is differentiable. It's a sufficient condition. So if this is true and this is true, then the function is differentiable. We actually don't know if there are other conditions that could lead us to the same results. We don't know that yet in the course, I should say. But as I said when I talked about this, it is fairly easy to check these conditions like we did over here. And for pretty much all the examples that we look at, they'll be satisfied. So, and why was differentiability such an important concept? Well, one reason is that it was an assumption here for the chain rule. And in the chain rule itself, we talked about at least a few ways to remember why this expression has the form it does. One of the main takeaways from here is that this is the one implicit variable case because we're assuming that it is possible to write z eventually as a function of t. And therefore that dz dt is a full derivative with the d's and not the partials. It may happen, though, that down here, the function z might end up being a function of two implicit variables, s and t. In that case, the derivatives are not going to be full derivatives, they're going to be partial derivatives. But the structure of the chain rule is very similar to what the structure was before, except that instead of this being dx, ds, it's now del x, del s, and same thing for the other terms. So that's a quick summary of this video, and I'll see you in the next module.